Thank you, David, for the introduction, and thank you for the invitation. So what I'm going to talk about today are ideas in dark matter physics, which are beyond the standard lore of where we should look for dark matter, where it could appear in signals. And part of it is motivated by the fact that we haven't seen signals in dark matter particle experiments so far. And so the question is, what are the places where we could actually hope to find these signals? And I'll try to highlight some of my recent work which tries to answer this question. Before we get there, just wanted to put these things in context. So the standard model of particle physics has been remarkably successful, and with the discovery of the Higgs, it's now complete, and you can extrapolate the standard model to very high energies. And so the question is, where do we expect new physics to show up? And I have this cartoon of where the new physics could show up, where on the x-axis I've written down the energy scales where it could show up, from all the way from the Hubble scale, the largest scales in the universe, to the Planck scale. And how strongly does it interact with us? So we know everything should interact with us gravitationally, and it could interact with us with some order 1 strength. And so this is supposed to be a cartoon which we would like to fill out to see where motivated physics lies. And to cut a long story short, there's a number of motivations that tell us how to populate this cartoon. And there's physics around the weak scale motivated by some notion of the hierarchy problem of the weak scale. There's, of course, dark matter, which is going to be the focus of our talk. At the Planck scale, we know quantum gravity, some theory of quantum gravity should show up, and perhaps in the form of a string theory. And we have even some indications that maybe physics at a much lighter scale could show up and is motivated. And experiments push forward this discovery frontier along this cartoon arc. And as we push forward using a number of experiments, we hope to see some of this motivated physics. And I'd like to highlight that there are experiments like colliders, which are traditional particle physics experiments, but also astrophysics and cosmology experiments, like the CMB experiments or dark matter experiments, and tabletop experiments like axion searches, as well as, of course, now gravitational wave detectors, which all come together to help us understand what is going on in fundamental physics. And so this is really an opportunity for different communities like cosmology, astroparticle physics, astronomy, particle physics to all come together and try to make sense of what is actually going on in fundamental physics. And that has been a part of motivation of my research so far. Today, what I'm going to focus on in this landscape is the problem of dark matter and how we go on to search for it. And if there are any questions at any point, please feel free to stop me. So this is a slide which I'm sure everyone has seen multiple times. The evidence for dark matter from its gravitational interactions is overwhelming. And it comes to us not from one particular place, but a number of independent measurements strewn across different epochs in cosmology. So there's evidence from Big Bang nucleosynthesis, of course, from the cosmic microwave background. And from more recently, if you look at galactic rotation curves or systems like the bullet cluster, we see that there is need for something, some kind of energy, matter density, which is not accounted for by ordinary baryons. And a kind of dark matter, remarkably, fits together well with all these indications. So it seems almost inevitable at this point that there's something which is dark matter in our universe. But what it is far from being clear. So there's a really large number of particle physics ideas for what dark matter could be, and this somewhat messy cartoon is supposed to illustrate that there really is a wide variety of ideas out there. And in principle, the mass of the dark matter could span many, many orders of magnitude. So dark matter could be as light as 10 to the minus 21 eV. Lighter than that, dark matter won't fit in our galaxies just because of its Compton wavelength. de Broglie wavelength, and it could be as heavy as stellar masses, with almost all the way through in these many orders of magnitude. So in principle, dark matter could be anywhere here, and in pockets of this large parameter space, we have some ideas where it could reside. If the mass of the dark matter is below, say, an EV scale, then we know that dark matter cannot be a fermion. It has to be bosonic. It's likely produced from a non-thermal mechanism in the early universe. And here, the description of dark matter really is of classical fields rather than particles, because the occupation number per mode is large. Conversely, if the mass of the dark matter is above the Planck scale, then it cannot be a fundamental particle, but it can be an accumulation of particles, just like planets or stars or primordial black holes. And so dark matter candidates above this scale are somehow composites of more fundamental constituents, or black holes. And in this intervening regime, we could have particle dark matter, a lot of models assume particle dark matter, and one particularly prominent candidate is weakly interacting massive particles, or WIMPs as they're called. Okay, so the plan for today is going to be the following. I'm going to introduce a few examples of WIMPs and demonstrate that there's a fundamental tension in WIMPs with direct detection observations, or lack of observations in direct detection experiments. And I'll introduce two particular ideas which can explain why we haven't seen dark matter in direct detection experiments so far. One goes by the name of flavored dark matter, and I'll explain what it means. But the idea is that there are multiple copies of dark matter, just as there are multiple copies of ordinary matter. And the other idea is darkly charged dark matter, which is a model where dark matter, in analogy with the standard model, it's very much like a QED theory where dark matter has its own dark photon and it interacts with dark photon. And so there is a WIMP miracle in this model as well, but it does not directly give rise to direct detection signals. And I'll go through this first part in more detail shortly. For the second part of my talk, I'm going to talk about sub-EV dark matter. So this part of dark matter that is bosonic and is described by fields, and the most prominent candidates there are what are called axions and dark photons. And I'll demonstrate how new cosmological mechanisms can open up parameter spaces in axions. In particular, for axions, I'll explain all of these terms in more detail in a few slides, but you can access large FA axions which are motivated by theory. And for dark photons, there has been an open problem of population of dark photons in a certain mass range, and so I'll present this mechanism which can populate dark photon in an extended mass range. And again, I'm going to go through these in more detail, but I wanted to lay out the plan at the beginning. Okay, so let us begin with the idea of WIMPs. And again, most of it is going to be review for most of you. The idea of the WIMP is that if you have some dark matter particle that is interacting with some standard model particle, and I've here modeled it as some 4 fermion interaction, and the strength of this 4 fermion interaction is parameterized by this number G dark in analogy with G Fermi, the weak interaction. So if there's an interaction of dark matter with standard model like this, the dark matter abundance, the correct dark matter abundance is obtained for weak scale interaction and weak scale masses. So about TV here is the weak scale. And so this is known as the WIMP miracle, where we expect new physics to have something to do with the weak scale, the scale of the Higgs boson and so forth. And so if dark matter is associated with this new physics, it automatically gives us the right Rayleigh abundance from a thermal history. So that makes it a compelling model. However, there's been a tension between the WIMP miracle and direct detection. If I take this interaction, the same weak strength interaction, and try to calculate the WIMP nucleon cross sections in our underground experiments, I find that it's literally off the charts in this exclusion plot. So these exclusion plots are the mass of the dark matter and on the x-axis and the cross section on the y-axis, and these interactions produce cross sections that are that were excluded even a decade ago. And so this is of course a very naive, almost dimensional analysis kind of argument, but you see that the tension is so severe that even extended models have trouble explaining the WIMP, sustaining the WIMP miracle while explaining the lack of observations in direct detection experiments. And so I'll present these couple of ideas that I mentioned, which sort of naturally fit into the WIMP paradigm, but explain why we haven't seen anything yet. And so the first idea that in that category that I want to present is called goes by the name of flavored dark matter, and it's motivated by some particle physics considerations, which I'll quickly go through here. So if we have this interaction of dark matter with standard model, we could close the loop, and we could get interactions between different species of standard model. In particular, we could get what are known as flavor changing processes, which are very severely constrained. And we cannot have flavor changing processes occur at the weak scale, as the WIMP miracle would imply. And so the general solution for this kind of flavor problems goes by the name of minimal flavor violation, which essentially restricts what kind of couplings you can have to different flavors of standard model. And for example, if this interaction really comes from an interaction of the dark matter chi with standard model quarks and leptons and some mediator phi, then there has to be certain flavor pattern. In particular, since standard model has a flavor index here, 3 flavors of standard model, either chi or phi have to carry a flavor index. And so the simplest model people have always studied is inspired from a supersymmetric model where this new particle phi is the particle which carries color and charge in order to balance charges here, as well as flavor quantum number. So there's multiple copies of this mediator phi. But there's an equally simple possibility that the flavor quantum number is actually connected this way, so that we actually have multiple copies of dark matter with flavor specific couplings to the standard model. And this in detail, this is what the flavor specific coupling looks like. But essentially, you should think of that we have one dark matter candidate that couples to the first generation, another dark matter particle that couples to the second generation, and a third dark matter-like particle which couples to the third generation of quarks and leptons. So this is a simple enough possibility, and it could well be that the ambient dark matter around us does not couple to first and second generations, but it actually couples only to third generation. So the third generation dark matter is the lightest and it's around, and so it won't talk to neutrons and protons or xenon, which our experiments are built out of. It would rather like to talk to third generation.
I understand more kind of Chinese question. Are those mostly neutrino-like things or mostly quark-like things you're going on?
Here?
Yeah.
So here, the standard model, these are quarks, for example.
Quarks,
right. So yeah, for neutrino, flavor violation is much less severely constrained. But for quarks, if you have general flavor structure here, so you don't impose some kind of MFV type structure, so at the weak scale, you're not allowed to have these interactions. So WIMPs always come with a flavor problem, which is which in supersymmetry theory people call it the SUSY flavor problem. But in general, to have weak scale interactions, you always need to worry about flavor structure. And there's 2 ways to solve it, and one is flavored dark matter. So this is sort of the motivation for thinking about these models. But as soon as you think about multiple copies of dark matter, they give rise to completely different phenomenology from usual standard model usual dark matter models. And so there's, I won't go into details here, but there are dedicated collider searches for these models now. They give novel phenomenology for indirect detection, like gamma ray signals. They can also give interesting X-ray lines, such as the 3.5 keV line, for example. And I'm happy to talk about these offline with people. But I just want to point out one particular aspect which is interesting, which I've been emphasizing. This is actually a promising target for current direct detection experiments. So since our dark matter, which I've labeled Chi-B here because it talks to B quarks in this particular model, since our dark matter does not talk to protons and neutrons directly, it only talks to B quarks, the only way it talks to protons and neutrons is through this loop suppress process. So you close a loop of B quarks, attach a photon, and this turns out to be the dominant diagram. And so we can redo our dimensional analysis estimate of the WIMP nucleon cross-section for direct detection experiments. And so we have this G dark squared as before, but now we have an extra loop factor just coming from this loop. So that goes like sort of alpha squared. And so that loop factor brings us down exactly to 10 to the minus 46 centimeters squared couplings for weak scale G dark. And so what this is saying is that even though tree level scattering of protons and neutrons has been ruled out a long time ago, if it turns out that dark matter only talks to protons and neutrons at one loop, we are only just now probing those kinds of models. So current and future experiments actually are these are the models which are interesting models to probe, which are not tuned by hand to hide from direct detection.
So if this thing falls to the top and really all that changes a step long, and the story doesn't change all that much.
Yes, if it did talk to top, then this diagram is identical except for what happens to the log. But when the stops running in the loop, the Z exchange actually also becomes important because of some kinematics. Here, the Z exchange is somewhat suppressed because MB versus M top and Z masses. So it's actually people have considered sort of this top flavored dark matter kind of model where that actually becomes also important. Okay, so the second example, and the whole example is on this slide, so I apologize that the slide is a little more crowded, but I think it's nice to actually put all the ideas in this slide to highlight the phenomenology. The second idea is that perhaps the dark matter is not actually interacting with us very much at all, and the whole WIMP miracle, quote unquote, is happening in the dark sector. So we still need dark matter to annihilate into something so that its energy density it's depleted, but this something could be some dark sector particle, and this dark sector particle has to be light, preferably like radiation-like, so that this energy density does go away. So a very simple possibility is that dark matter is very much like the standard model. It's like an electron or a proton that talks to its own photon. So it's this first model we consider in quantum field theory course. It's a QED-like model, and the dark matter can annihilate into a pair of photons, and for weak couplings that precisely recovers the WIMP miracle where we get the right relic abundance of dark matter. But the presence of this light mediator brings with it some self-interactions of dark matter, just like electrons and protons have strong self-interactions. This dark matter would no longer be collisionless, and it would indeed be a self-interacting dark matter model. So it can perhaps resolve small-scale anomalies in cold dark matter that people have put forward. It can have observable effects on galaxy shapes. And there's maybe this is a slightly more technical point, but the velocity dependence of this self-interaction is such that you actually get into a strongly self-interacting regime as opposed to most self-interacting dark matter models people have built. And so this actually has interesting consequences for shapes of galaxies of different sizes. So I should explain this cartoon on the right side. This is now a cartoon of going from the early universe down to today. And what these arrows are demonstrating are different aspects of this kind of idea have implications for phenomenology in different parts of cosmology. So charged dark matter can give you a WIMP miracle, but it also gives you variations in halo shape. So it can give you chord, or it can give you self-interactions, and affect the sphericity of halos, for example. If, again, in analogy with the standard model, on top of this particle X, we had a counterpart of the dark electron. So a light particle that is also charged under this dark photon, that dramatically, again, changes the cosmology and astrophysics of this model. Through this particle C, the dark matter particle strongly couples to the dark photon fluid, much like the CMB, where protons couple to photons strongly through the electron. So now you actually end up with the phenomenon in the dark sector, which is termed dark acoustic oscillations, where the fluctuations in the dark matter itself oscillate with the dark photon, and that can lead to a damped matter power spectrum, which is again something which can help with small scale problems in principle. And the presence again of this light particle enhances dissipative processes, much like cooling in the standard model. The presence of dark electrons can lead to cooling in the dark sector. And so this can actually lead to cold, cooler dark sector objects, which can collapse to form disks or other collapsed structures, and which can again be observable. If this is some subcomponent of dark matter, then we could perhaps look for these collapsed structures in the dark sector. Finally, if this dark photon or this dark sector does couple to us very feebly through a portal to us, the portal usually means there's some very tiny coupling between the dark sector and us. It can actually, and this work was some of the earliest work on this kind of portals was done here at U Toronto. This portal to us can actually give us, again, new signals which are unexpected. So we can get annihilation signals of this dark matter from these collapsed structures. So these would look like point sources. Typically in dark matter physics, we don't expect annihilation signals to look like coming from point sources, but these collapsed structures would mimic point source morphology. So again, this is a somewhat fast review of a bunch of ideas here, but the idea is to show you that even in this sort of nightmarish scenario where dark matter doesn't couple to us very much at all, cosmology and astrophysics signatures can actually give us a hint about the nature of interactions of the dark matter within the dark sector itself. So no questions about this, I guess. Okay, so I'm going to switch gears, and now I'm going to talk about the second part of my talk, which is bosonic sub-eV dark matter. So again, to remind you, this cartoon where by sub-eV dark matter I mean sub-eV dark matter masses below eV, and consider new ideas in their cosmological evolution. So a number of very well motivated models actually fall in this category of sub-eV dark matter, and the categorization essentially relies on the explanation of why are these particles so light, why are they below the eV scale, and often they're light because they are Nabu-Goldstone bosons of some global symmetry. So the canonical example, a very well motivated example, is the QCD axion, or in general more axion-like particles, which are all light because they're pseudo-Nabu-Goldstone bosons of some global symmetry. You could naturally have light spin 1 particles. You could indeed have massless spin 1 particles like our photons, but we could also have massive but light spin 1 particles. And I'm going to phrase them very very roughly as dark photons in this talk. And finally, we could have scalars which are very weakly coupled to us. And since they're very weakly coupled to us, they can be naturally light. So usually things like modulus or dilaton fields fall under this category, that they're very light, very weakly coupled scalars. And all of these very light particles are potentially dark matter candidates. And since they are not particle-like dark matter, where you can build an experiment where they scatter off and deposit energy, these require a completely different strategy to go after these. And likewise, there's no thermal history which produces such light particles and makes them cold, or at least there's no simple thermal history that does that. So their cosmological production also needs to be specialized. And these particles, by the way, occur ubiquitously in theories of quantum gravity, theories with extra dimensions. So when you compactify extra dimensions, you typically end up with a bunch of axion-like particles, spin-1 particles, and the size of the extra dimensions sort of become the modular dilaton fields. So these, if you do think that there's something like string theory in the far UV, they produce these very light particles as a consequence. Okay, so one of the most well-motivated candidates among these candidates is the QCD axion. And the QCD axion is motivated as a solution to the strong CP problem. I'm not going to go into details. I'm happy to talk offline. But the idea is that we measured this one phase, the strong CP phase, or rather constrained it to be this extremely small number, whereas the CP symmetry in the standard model is not a good symmetry at all. So there's no reason a priori for this number to be so small. And the axion, the QCD axion, is designed to solve this problem of explaining why this number in the standard model is this small. And the idea is to make this parameter in the standard model, this phase, a dynamical field. And then the QCD the quantum chromodynamics generates a potential for the axion, which automatically drives it to 0 values. So the potential for this for the QCD axion is minimized at theta equals 0. So even if in the early universe it was set away from its minimum, it's going to go down dynamically to 0. And so if this parameter is not a parameter that's fixed, but it's actually a dynamical field, it naturally goes down to 0. And this parameter FA here, so F pi, M pi are just particle physics parameter that we've obviously, that are all well measured. And so there's only one free parameter in this model, which is this parameter FA, which is the decay constant of the axion. So all its couplings and its mass, for example, are just set by this one parameter FA. And so FA is one parameter that sets all of the phenomenology. And indeed, this is while solving a fundamental problem in the standard model, it's also a very promising dark matter candidate. And the dark matter abundance of axion, luckily, only depends on a few details of cosmology. There are a few mechanisms that work to populate the axion dark matter. The simplest, perhaps, is a misalignment mechanism, which says that if you set the axion far away from its minimum in the early universe, at some point it starts oscillating. An oscillating scalar field has the same properties as matter. It redshifts like matter. It clumps like matter. And so it's a dark matter candidate. And its energy density is just set by the energy in that oscillation. There's another mechanism, which is production from topological defects, which I don't think I'll get into for the purpose of this talk. But that is also one of the canonical mechanisms by which axion dark matter gets populated, depending on its early cosmological history. And while I will focus mostly on the QCD axion, axion-like particles, even though they're less motivated because they don't solve the strong CP problem, they're equally good candidates for dark matter. So it could be that something else solves the strong CP problem, but the dark matter is made out of particles, axion-like particles, which I remind you appear ubiquitously in theories of quantum gravity. So there could be multiple axion-like particles which are light, and a number of them make up the dark matter, for example. So I'll focus on the misalignment mechanism to populate the axion dark matter. And so in the early universe, the axion is displaced from its minimum somewhere. And for the QCD axion, the axion potential itself at very high temperatures is turned off. So these dashed lines are showing that the early universe, the potential is basically flat. And as the universe cools around the QCD phase transition, this potential develops and becomes its zero temperature value as we see today. And so this is the solid line shows the axion potential today. And around that time, the axion starts oscillating around the minimum. Its energy density is given by the harmonic oscillator energy density. So it's given by just m squared, which is its mass, times the field value squared, which is Fa times some initial misalignment. So its initial energy density is basically just given by amplitude squared times mass squared, as you'd expect.
Ask a quick question about
Sure.
the development of potential and that it is associated with phase transition of sorts. The mantra is instanton effects magically give this. Do you have a good physical feel of exactly what's going on that is causing the potential to do this dip, which is so fundamental to the axionic story? I mean, there may be other mechanisms, but it's the instanton magic, which is often invoked.
Right. Let me think for a second for how to best answer that question. So yeah, I mean, I guess I'm just repeating the words that go along with instanton magic here, but I'd say what you want to see when you say that this potential is either this solid line or this dashed line is what energy cost there is for the axion to be here versus here, and we can evaluate that at zero temperature, and we can evaluate that at high temperature, right? And so the statement is that for the axion to be at zero temperature is much less, the field configurations have much less energy cost than at high temperature. And the instanton magic business is that the instantons have a characteristic size, and if their instantons don't fit inside the Hubble horizon, or if the instantons if you're at high temperature, these instanton solutions are not solutions, not classical solutions at that high temperature bath, and so that so the instanton calculation, which tells you what this potential should look like, should be cut off at the appropriate temperature.
Well, often one thinks of instantons in terms of mini bubble creation or something, and yet presumably the only memory of any of that would be stored in the axionic potential energy density, which is an interesting phenomenon. But anyway, this is an issue that I've had for a long time, from time zero basically, on the axion magic of why the potential develops exactly as it does. Anyway, so something we can discuss offline.
Yeah. Right. Let's discuss offline, because I don't think I have a better answer than the one I gave. But I think it's a good question. That yeah, let's discuss offline. But the short answer that I know of is that you're supposed to cut off the instanton size at the temperature you're evaluating. If that temperature is much above the QCD phase transition, then you're cutting off the instanton at a weak coupling, and so those contributions all the QCD contributions are exponentially suppressed. So very high temperatures, you're basically in the quark gluon phase. It's a weakly coupled theory, so that doesn't have a big contribution to the axion potential. Okay, and by the way, if this was not the QCD axion but some axion-like particle, then this story of development of the potential is irrelevant. This potential is always just turned on for a axion-like particle. There, yeah. And so the axion-like particle again starts oscillating when its mass reaches the Hubble scale. That's when it goes from slow rolling to oscillating, and then its energy density is again given by its initial field value squared times mass squared.
Except if the axion-like particle gets its potential from some other confined center, then everything will transfer it somewhere, right? Or are you saying that?
That's true. So this is true. The times where these two things happen, by two things I mean development of this potential and starting of the oscillation of the axion, so H equals m, in principle are not necessarily close to each other. Now for F close to m Planck, they happen to be on top of each other because, so in principle, even if, this development of the potential could happen at very high temperatures and the axion could start oscillating much later. And so this development of the potential is irrelevant, at least to the onset of the oscillation of the axion. So maybe another answer to Dick's question is that one way to think about high temperature field theory is to compactify the field theory on a circle. And now your instanton solutions for very high temperatures, the circle is really small. And so your instanton solutions don't fit in that circle. And so you have to cut them off. And so so the cut off instantons are suppressed relative to the vacuum instantons, which are in the decompactified limit. Maybe that, I don't know if that picture helps, but that's another way to say it. Okay, so we have some energy density initially. Once we know what the initial energy density is, we can evolve it in the universe. It turns out the number density, you don't produce any more axions once it starts oscillating, so that number density is conserved. And so we can just track the energy density to today. And what we find is that the energy density in the axion is correct, is the right Relic abundance if this one parameter f is 10 to the 12 GeV thereabouts for some order 1 misalignment angle in the early universe. So that's actually a very, very interesting result, because we said Fa is the only free parameter in our QCD axion model. And now we're saying that if we take a generic point in parameter space, the early universe doesn't know about where this minimum is going to be, so the axion is some order 1 misaligned from this value. It actually picks out a value for Fa for us. So we have a very narrow target space for where to look for axions. So one question is the target space really this narrow, or can we get away from this very specific value of Fa of 10 to the 12 GeV? One way people often talk about is to just say maybe theta I is just artificially small. It's a very tiny number, so you can get much larger values of Fa. And to explain why that theta is small, maybe it's tuned, maybe it's anthropic, so that you can try and explain away why theta is small, but maybe that's not the most compelling explanation. By the way, Fa of around gut scale is very well motivated from, again, stringy models. So usually if you build a stringy model, then the Fa that drops out is around the gut scale. So if we could have a cosmological mechanism that makes 10 to the 15, 10 to the 16 GeV viable without tuning, that would be of some value. And so I'm going to show you such a mechanism. But any other questions about this before I go on? Okay, so the mechanism that lets you go towards larger values of Fa than the naive misalignment would indicate goes by particle production or tachyonic particle production. And this mechanism comes up a lot of times in post-inflationary reheating, or sometimes it's called preheating, but they're all similarly related ideas. And so the idea is to couple the axion to a dark photon. And for this case, for now, this is a massless spin 1 particle that we're coupling the axion to. So the axion coupling, if you're probably familiar, you've looked at this before, that it looks like the axion couples to the QCD field strength glue tilde. What we're adding is a coupling of the axion to a new spin 1 particle, which is the dark photon. So it couples like AFF tilde. F dark tilde, which is the field strength of the dark photon. And the idea is that as the axion starts oscillating, it depletes its energy into these dark photon, which are radiation, and so they redshift away. So they basically reduce the overabundance of axions. And this process of depletion of the energy into dark radiation is rather violent. And the way to see it is to say, in this time-dependent axion background, so that the oscillating axion is just some time-dependent background, let me try and write down the equation of motion for this dark photon field. And so that's what this equation of motion looks like. For some k mode of the dark photon with polarizations plus or minus, this is the equation of motion. For a usual massless field in conformal time, you would get a double prime plus k squared a equals 0, which is the usual dispersion. But in the presence of this coupling and the time-dependent axion field, sorry, my notation is switched between these two. Phi is just a. Slide was made at two different points in time. So sorry, phi is just a. So the time-dependent axion background introduces this extra term in the dispersion for the dark photon. And so if you look at this wave equation, this is the effective frequency of this oscillator, and this frequency, depending on the sign of the polarization, can actually be negative for a certain range of k values. And so some of these modes are unstable. The phrase we use is tachyonic instability because it's a negative frequency squared. So some of these modes of the dark photon will rapidly grow exponentially from initial seed fluctuations. And so by this mechanism, they would deplete the energy density in the oscillating axion fields and absorb it in this dark radiation. So any questions about this mechanism?
So presumably as you deplete the axion field, this tachyon term vanishes, and at some point just let the normal dark photons after the axions die down.
Let's see if yes, so here, precisely that's what happens. What you need for initially for this, right, so let me just describe the evolution, and that's exactly what happened. What you said is just what happens. So the k modes that are tachyonic are roughly given by beta phi prime over fa, so this number, which is essentially beta times mass of the axion times some initial misalignment angle, because phi prime is roughly f times mass of the axion, and so this is just beta times mass of the axion. So what you need is beta to be somewhat larger than 1, order tens, for this mechanism to work. And the reason is that your source term, the axion, is oscillating on the time scale of ma. The frequency of the axion is ma, and your growth exponent is beta times ma. And so if you want substantial growth to happen, you want the growth rate to be, you want the exponent to be somewhat larger than the oscillation time scale, and so you want beta to be order tens, and then you get a big burst of particle production. Eventually, phi prime redshifts and produces axion, so it also depletes its amplitude. So at some point, this amplitude becomes smaller than 1, and at which point the production becomes inefficient. So the production is efficient as long as this beta times the field value times ma is bigger than ma, and so that stops as the field redshifts away and beta becomes small. And I'll show you numerically what happens. The other thing that you see is that if there was a mass term here, that mass term would be an additive term, and that if that was big, that would just completely quench this instability. So that's why you couldn't use a standard model photon itself to do this. Because there's a big thermal mass, and so that's why there was a dark photon with no dark charged particles around, so that there's not an extra big thermal mass term here. So far so good?
The whole reason why you're doing this is to have a wider range of FA.
Yes.
To avoid axionic constraints that exist.
It's not constrained, but if we just took Yeah, so if I just took Fa to be 10 to the 16 GeV and some misalignment angle of order 1, I would have too much dark matter.
Oh, but it's a free parameter, but anything you want, and what's wrong with 10 to the 12?
Oh, no, there's nothing wrong with 10 to the 12. But then, so we are building experiments, and we have built experiments to go after the 10 to the 12. Now the question is, let's say I have an idea for an experiment that can only look at 10 to the 16 GeV experiments. And this is not a hypothetical. This is actually the case, that there are experiments which are only sensitive to dark matter axions of 10 to the 16 GeV because their masses are different and the couplings are different. Now the question is, do they always rely on tuning of this initial misalignment angle, or there are mechanisms to populate them? That informs my decision of how compelling these experiments I think they are.
I mean, similarly, you could come up with a theory why the tuning is natural.
So the only, because this is such an IR, so you would certainly come up with a way to maybe relax it in the early universe and make it go closer to the minimum. But you have to have a very low temperature phase in the, it's not easy because this is a very low temperature quantity where the minimum is. It depends on the quark masses and phase in the quark mass and so on. So the minimum, where the minimum is a very IR quantity in some sense. And so the early universe usually doesn't have, in a simple model, doesn't have access to where that minimum is. So you don't even know where you want to start, except if you put an IR constraint like anthropics, or you say something like, maybe in the early universe it was very cold and during inflation somehow I had a mechanism.
Adding a new interaction, a new particle, I can usually a V of theta, can't I?
So, no, what I'm trying to say here is not that this is motivated necessarily, or I'm arguing for the possibility. No, the gut scale is motivated.
That's why indeed. So you pick a scale, and now you're not going to reconcile this overproduction, and your mechanism is to have to decay some dark radiation.
Yeah.
But it must have been considered the case where FA is larger than the inflation scale.
Yes.
What happens there?
So this misalignment mechanism is applicable for the cases where the axion, the PQ symmetry breaking happens before inflation. So the axion potential is, the axion is a massless particle already during inflation, and so all our observable patch picks a particular value of theta. The alternative possibility that you're alluding to is that the Peche-Quinn breaking happened after inflation. So during inflation, the potential was like a bowl, and after inflation it became Mexican hat-like. And so different patches of the in that case different patches of the universe ended up with different value of theta. So maybe I should draw it. So if during inflation your potential was like this, so you were stuck here in the field space. This is a Mexican hat potential. After inflation, as you develop this potential, the field would fall over different places. And so different patches would have different values of this axion initial misalignment, as you know. And in that case, what the dark matter abundance is given by is actually some ensemble average of the theta I squared, which is some order 1 number, pi squared over 3 or some order 1 number. And in that case, there's actually a very precise prediction of what the axion abundance should be. So it's not sensitive to the initial misalignment angle. There's no freedom in choosing the initial misalignment angle because you populate all of them in some random fashion. But there's a complication there because as you fall off this potential, you also make topological defects because you make axion strings which wind around the potential, and so there's some numerical simulations needed to figure out what the axion abundance is, and there's some amount of debate about whether that is a reasonable, what the answer in that case is. But, so that's an orthogonal question of what happens in that case. So here I'm just focusing on the misalignment case, and there is some freedom to just tune theta I to 0. Sorry, question?
So this is talking about how FA is very tightly constrained to the QCD axion. Are there similar constraints for just generic axion-like particles, or is there more freedom there to set FA values?
Good. So that's a very good question. So the reason that only FA matters here for QCD axion is because the mass of the axion itself is set by FA in the QCD case. The corresponding expression for an axion-like particle involves both FA and MA, which are both free parameters. So you have an extra free parameter, and so there's a two-dimensional parameter space where you get the right relic abundance. And again, there's obviously a misalignment angle as before. So there is some more freedom in the axion-like particle as opposed to the QCD axion. But just to go to just to answer Welly's question again, I'm not saying that this mechanism is actually. I'm not trying to push for this mechanism, saying, look, this is what could be going on. We should look there. Just trying to see. This seems like a sort of robust prediction. What would it take for us to go to larger values of FA? You could tune. You could make other mechanisms to make theta I small. What are the? Let's just make a list of all the mechanisms that work and decide whether those are compelling or not. So, and I agree with you that this is not. It is hard to start from axions and deplete them into some energy density very quickly because you don't have too much time from QCD phase transition to say BBN or something. So you need some explosive mechanism. So I think it's cute, but I don't think it. I do think it has too many moving parts to actually say this is what's going on. It's a possibility, but.
If the mechanism in general has to be fairly explosive, would there be like one little like even if there was anything that would be that explosive?
Right.
Gravitational wave signature or something?
So I don't know if people have looked at this particular. People have certainly looked at gravitational waves from particle production. I now don't remember from the top of my head which parameter space is most promising. But for one thing, you do expect large fluctuations in the axion field. So let me come to that. The second thing, but you expect a signal which is large fluctuations in the dark matter field itself. Is that roughly satisfactory, or you're still skeptical? No. Okay, good. But I agree with the sentiment that you see if it takes too much work to do, then it's not compelling, and I don't want to push for it too much. And once you make an explicit, concrete model, then everyone can make up their mind about how compelling it is. Okay, so we talked about this. So let me show you what happens. And here, what I'm treating the axion as a spatially uniform oscillating field, and seeing how and neglecting the fact that if at some point this approximation of a spatially uniform axion is not valid anymore. So neglecting this backscattering into axion K modes, this is what you get. Here I've plotted the axion field amplitude scaled by some scale factor such that it's constant, so it's visually easy to follow. The gray line is what would happen for a QCD axion with this value of FA without this coupling to dark photon, without this depletion. And the green is what happens once I add this coupling to dark photons. And so you see that initially it's oscillating as it would, but eventually this production of dark photons comes up and quenches the axion oscillation dramatically down to smaller values. And you can see this happening also in the energy density, where I've scaled the energy density by their corresponding redshift. So they're in the absence of any particle production, they would be constant. So the axion is multiplied by a cubed and dark photon by a to the fourth. And so the axion again is initially its co-moving energy density is roughly constant, and at some epoch the dark photons which are being exponentially produced from seed fluctuations catch up to become significant, and then the axion energy density drops down significantly by a factor of almost 10 to the 5, 10 to the 4, and after a certain point, the axion this particle production process becomes inefficient, and so the axion and dark photon just this process stops, and they retain their co-moving energy density. But you could start with an overdensity of almost 10 to the 4, 10 to the 5, and quench it into the dark photon.
Why does the dark photon energy density seem to not change?
Seem to not change when here? Why is it not going? Yeah, I mean there's local energy conservation always. This is multiplied by a to the fourth, and this is multiplied by a cubed, but locally the sum of them always locally there's always energy conservation. So
What's your R?
sorry, R is beta. Sorry, I should say, yeah. Here I managed to overlay them, but here I guess somehow they moved. If I moved, then I've moved a lot.
So as you change beta, it happens, you shift the line, you shift the whole mechanism to earlier times, is that what happens?
As you shift beta, the typical momentum that you're producing is ma beta, and the growth rate is also ma beta. So the whole thing moves left. Right.
So the bottom one is happening, the beta is the same. So
Yeah, beta is the same. So this is happening at roughly the same time. I think they're aligned even. Well, they're not quite aligned in temperature. They're not quite aligned. So, but they should be happening at roughly the same time. Around 100 MeV is when you start noticing the difference. In fact, so here again, this is neglecting backscattering. You could get so many dark photons eventually that you actually start being sensitive to them in experiments with delta ineffective. You produce so much extra dark radiation that you actually will notice that around CMB time.
it's essential that the dark photon have enough mass? Is that why it has to be dark?
So it's essential that dark photons don't have a thermal mass.
Not.
Yeah, because this.
Why did you say you could use the standard one?
Because the standard model photons would have a thermal mass. This is around QCD phase transition.
Oh.
And so their masses are around QCD temperature. And these K modes are like around Hubble, around QCD. So the thermal mass would completely quench any of this instability for a standard model photon. So you use the dark photon precisely to not have a mass.
So you really have to dump into an empty, sterile dark sector.
Or something that was, the charged particles are all heavy and annihilated away and whatever. You could have dark photons around from that sector, but you shouldn't have light charged matter thermalized. That would quench this, basically. Good. So, but I've been emphasizing that this is all neglecting backscattering into axion K modes, and at some point this is no longer a valid assumption. So at some point these produce so many dark photons that many to two axion particle production becomes important, and so the axion condensate starts to fragment. And so this is one thing that would always happen, I think, that eventually you'll end up with a fragmented condensate rather than a smooth condensate. So at some K scale, you would have big fluctuations, which you would not expect for a QCD axion. And so you could make compact objects like mini clusters and things like that. And so that fragmentation, but all that fragmentation also arrests this process. So it's not, to do the fragmentation properly, you actually have to run a lattice simulation, which these people have subsequently did run for some parts of parameter space. And so, like I said, the higher number of dark photons would scatter back into axions, and so you need a lattice simulation to figure out what happens. And here, I've plotted the axion number ratio to the initial axion abundance to the depleted axion abundance divided by the initial axion abundance, and relative to the case where there was no particle production. So this would be 1 for no particle production, and on the x-axis is this parameter beta that Eli was asking about. And so for small values of beta, like I argued, there's no real effect. There's no particle production. And for some values of, and this is the results of their lattice simulation of these people. So for small enough values of beta, there's no appreciable particle production. But for around beta order 10-ish, 10 or 20, you start seeing that the number density is depleted relative to the uncoupled number density. But then there's a saturation point after which the backscattering effects become important, and then you don't trust the calculation I showed you before, and so there's some maximum amount of depletion you can reach. And so the conclusion, these lattice simulations are not cheap to run. They're somewhat computationally expensive, and so the conclusion was that maybe 10 to the 15 GeV is the maximum you can get to in these in this mechanism. You can't get to all the way. Okay, so in the last 5 minutes, let me tell you about the mechanism to populate dark photon, dark matter. Luckily, the physics mechanism is exactly the same. The motivation is slightly different. The idea is that dark photons spin one fields, but now with which carry a tiny mass could themselves be dark matter particles. So this is again, this is a separate possibility from the one I've just described. Here there's just a dark photon field with some mass, which is dark matter. The interesting thing is that if you calculate the electric field in this dark photon locally by based on the amount of dark matter we know exists, the dark electric field is around the electric field in a plug-in socket. It's about 50 volts per centimeter. So if we had a dark matter plug, we could just charge our phone using dark matter, plugging into this dark photon. And there's an open question of how to populate dark photon dark matter. Setting it away from its minimum in the early universe like we did for the axion doesn't quite work because it's a spin 1 field, so that energy density doesn't stay fixed until it starts oscillating. It depletes away. And really, the only mechanism, there's some limited inflationary production mechanism that only works for dark matter masses above 10 to the minus 6 eV or so. And so here I've shown two parameter spaces of these dark photon dark matter models. One is a B minus L gauge boson, another one is another motivated model, which is a dark photon that kinetically mixes with us. And the parameter space goes from something like 10 to the minus 20 EV all the way to GeV energies or so. But you see that this mechanism, the only mechanisms available, operate in this part of parameter space if Hubble is exactly at the bound with currently constrained at. If Hubble is smaller, then the masses become even heavier. And so there's all this parameter space which actually experiments like LISA or LIGO would be sensitive to, or future experiments like atomic interferometers or torsion balance, future torsion balance experiments will be sensitive to. So these are interesting parts of parameter space, but there's not a way to populate this part of parameter space. And so similarly for dark photons, there are experiments designed to look for these dark photons. It's not clear where they would get populated in this part of parameter space. And so I'm going to use the same mechanism I just showed you to make all of this part of parameter space viable. And so the idea is to couple the dark photons to an axion-like particle. So then the dark photons are coupled as before, but now they have a mass term as well. And the energy density initially is stored in the axion. So I've misaligned the axion, and it's stored in the axion. And as the axion starts to oscillate, it dumps energy into dark photons using the same particle production mechanism. And so the equation of motion now has this mass term. So if this mass term is really big, like we said before, this will not work and it will quench the instability. But if the mass term, and we'll see in a second how it looks like as a function of mass, if the mass term is not too big but not too small, then the dark photons that you produce could be dark matter. And so that would give you a way to populate these dark photons. And for whatever sociological reason, a number of papers appeared on the same day. Well, they appeared on the same day because we coordinated, but the four different groups were working on the same kind of idea, and they wrote us to coordinate, and so we coordinated. This is a lesson of why you should never forward cite your papers. In one of our collaborators' papers, we said, and this can be used to populate dark photon, dark matter as well to appear. And then the people who were reading all wrote to us, "Oh, we noticed you're doing this, so we are also doing this. Do you want to coordinate?" So forward citations are not a good idea. Okay, so.
That was a very politic way of claiming primacy.
Oh no, sorry, no, I didn't. No, we would have not coordinated. So maybe we would have gotten scooped. You're right. Yeah. So maybe it is a good thing. So, sorry, I should. So good. So this is again now this is now done fully with lattice simulations. I'm not making any assumptions, and these are the parameters we used for the simulation. And so initially, the blue line shows the axion, and the red line shows the dark photon. So the number density in the axion is depleted around the time the oscillation set in, and the number density in the dark photons take over. And as before, most of the spectrum of dark photons has peaked around k equals beta ma, and so here, let me not go into details, but this red line again is showing the dark photons versus the axion spectrum, and this solid line is at early times, and dashed line is at late times. So already at early times, by early I mean about ma tau of around 10, we've produced a lot of dark photons, but even after that, a lot of axions keep getting converted. So this solid line falls to the dashed line, whereas this red solid gets enhanced at this high K mode. So you produce a lot of you keep producing dark photons to even by the time you're here. And so this is the energy, this is the abundance of the axion in blue and the dark photon in red as a function of the dark photon mass. So we see that if the axion and dark photon masses are comparable, then this conversion of number density of axion to dark photon can give you the right relic abundance, whereas axions will form a subdominant component of dark matter. If the dark photon mass becomes order the axion mass, then this whole process becomes inefficient, and you get just axion dark matter back. And if the dark photon mass is really small, then it redshifts for a very long time as radiation, so you also get too little dark photon abundance. And so there's a sweet spot where you get the right relic abundance of dark photon.
Are there theoretical mechanisms to get the masses to be similar?
Maybe we had some, but they were clunky enough that I don't know if you'd call them that an explanation of anything. So yeah, so that I think is definitely a coincidence here. Coincidence of scales that you need. You need it within an order of magnitude or something, but you need them to be close to each other. Okay, so sorry for rushing through the last part. Let me just leave the conclusions up and just say that the lack of signals so far is pushing us towards going beyond the old standard paradigm of dark matter, and once we push on the old paradigm, we find new places to look for dark matter. Thank you.
Okay, so we've tortured Prateek quite a bit in the last hour and a bit. So maybe we have time for 1 or 2 quick questions before we go coffee upstairs.
Well, Uber question is, if you were a betting person, what would you bet on?
I think I would still bet on the standard QCD axion at this point. So none of these extensions that I talked about, not large values of FA. I think I would bet on 10 to the 12 GeV QCD axion, which the simplest models have not yet been ruled out, and we are now probing over the next few years. We're going to probe the parameter space, which is the canonical QCD axion. And so once that is ruled out, then I'd have to reevaluate my priors. But at this point, I think the simplest possibility is still alive and within reach. So I think that would be my bet.
But the QCD axion was brought in to try and solve the problem, and then magically there it is. But once you start to think about there it is, you think about a whole hierarchy of these directions that basically don't cost energy. So from that point of view, we more or less kind of an unconstrained possible spectrum, and maybe, I guess it's universally thought that the QCD axion is a strong CP problem, but but I guess what I'm saying is that the abundance of these angular directions
Could be huge, you're saying.
all sorts of interesting ways of
I guess you're saying is the model space so big that the small likelihood of any one branch is outweighed by how many possible paths.
maybe that's it. That the prior probabilities are not narrow, it's extremely large. It's only a question of data driving it down.
Do you want to have a Bayesian measure?
I just recall that very distinguished people have written about the axion and properties.
Right. So we'll check, yeah. So the anthropic axion is we'll check, yes. So I would say, so we agree that there's one parameter, however, which is FA, which defines the whole QCD axion story. We've ruled out everything, let's say below 10 to the 9 GeV or something by astrophysics. So FA could be anywhere between 10 to the 9 GeV and Planck scale. And now we could ask about our priors on those. If it's above 10 to the 12, 10 to the 13 GeV scale, then it seems generically you would get too much axions as dark matter. So it just seems in observational tension unless you do something. So if you say more words and if you say anthropic or you say something more, 10 to the 13 GeV and above is just observationally disfavored. So then it leaves you from with 10 to the 9 to 10 to the 12, 13 GeV, which I think is a reasonably narrow parameter space. And so it doesn't leave you in log space, at least doesn't leave you with too many orders of magnitude to play with. So I would say 10 to the 11, 12, somewhere around there is where my prior would be peaked, because it gives you not naturally dark matter. Right. It is based upon data after looking at it. Yeah.
Because you're an expert on making the axion do slightly different things from that sort of standard prediction. And
right.
If I'm not mistaken, some of the motivations are that you can have other theories where axions pop up, or maybe you want to put the axion to work in some other way, in some other mechanism, and then having a bit of flexibility about where to line that parameter space
right.
Is useful, because then that might be motivated from a different theory reason if it does some other job.
Indeed, yeah. Well, I mean, as soon as you claim that there's a relatively narrow target space, as I've just done, the question is how well do you know that this is actually that narrow? So you try to build mechanisms to say, well, what does it take to go away from FA of 10 to the 12 GeV? Well, you need some funky cosmology, maybe particle production, maybe you need tuning or anthropic. So the price to pay is rather large. If you say that it's naturally set to that value versus some anthropic selection, you have to bring a new principle. Likewise, if you want to say that axions always lie on this QCD line, what does it take to go off them? You have mechanisms. So we've built some mechanisms to do that. And again, you just look at the cost of what it takes. So I'd say that having done that exercise of trying to get away from this sort of narrow parameter space in axions, it does seem like a likely place for the axion to be. It's not easy to go away from this point. So given that we haven't even ruled out yet the simplest possibility, which I would say that's probably where I would bet my money. If I was a betting man, as Dick said. I'm not a betting man, so.
So maybe that's a good point to continue over coffee. So let's thank our speaker again.
Thank you.